Hello, and welcome to part 2 of the machine learning track. It is super good to see you. My name is Will. We will do formal intros in 2 minutes when we really get things started. But welcome. Oh, hey, Polar Void, Fleabag, good to see you. Yadav. It's so fun whenever I see usernames that I actually recognize. It is good to have all of y'all back. Hello, Stuart. Yes, the Kalimba is back. I am back. The flower crown is back. And today we are going to get into pushing some pixels around and having a lot of fun with our data. Last time we did our introduction, or I think for most people, honestly, review of Python. And today we are going to just look at really playing with image data. We're going to ask the kind of silly question, what is an image? And hopefully, if we have time, we'll take a peek at our actual data set that we will be playing around with today. In other news, I looked at all of our submissions from last week in that form. So one fun thing, most people, like 71% of people, said that we were going at a good speed. They gave me that 3 on the 1 to 5 scale, where 5 is too fast and 1 is too slow. And then we had one person who said it might have been a little bit slow, but then we had like 25% of people say it was a little bit fast. And so what I will say is, compared to sessions past, if you were here for init or any of the past Global Hack Weeks, we ramped up pretty quickly. And what I will say is that for this session, really the first 3 sessions are going to hopefully stay no faster, maybe even slower than our session yesterday. We will, of course, still be using Python, but we're going to introduce concepts pretty slowly. We're going to kind of, for lack of a better word, like play in the kiddie pool, sort of. And then in the 4th session, we will sort of bring out the big guns and kind of throw the kitchen sink at our problem. So today, we're going to learn how to play with image data. Next time, which I think is tomorrow, Wednesday. Wait, when is no? Okay, yes, the next session is on Wednesday. On Wednesday, we'll be building a sort of simple first iteration on a machine learning algorithm, and then finally on Friday, we will be pulling out TensorFlow and Keras and a bunch of fun tools. Somebody asked if we'll be using CV, and no, not explicitly. I'm actually not. I don't believe that Keras uses CV behind the scenes, but CV might be a dependency of Keras. So yeah, we'll be using CV specifically. We'll be playing a lot with, at least today, we'll be playing with matplotlib's im_show function, if you're familiar, which we'll take a look at a second. Let's see. Did you look into the TPU stuff on TensorFlow from the last Global Hack Week? Yes, I did actually. Yeah. Okay. So yeah, last time I put my foot in my mouth and said something rather silly, which was that Colab, if you were using Keras in Colab in sort of a vanilla way, that it would automatically hook up the accelerators for you, the GPUs, the TPUs, and that is not true. And so we will be, yes. And I think somebody called me out on it. I was like, oh yeah, I'm not sure. And I went and I looked into it, and you were totally right. Was it you, Polar Void? I think it was. You're totally right. And so we will look at the sort of the right way to do this on Friday. Yeah, no, thank you for saying that, because I would have gone on believing that, foolishly, that I was actually using the accelerator when I wasn't. Which I suppose if you give enough time and you run enough algorithms, eventually you realize, like, wait, this is not actually faster, If some of the words that I just said didn't make a lot of sense to you, do not worry. You have 2 more sessions before we really get to that stuff. Oh, hello, Samrid. It is good to have you again. I remember you. Akilu, it's good to have you as well. I'm so pleased you all came back. Also, Key Goodson is the only person that sounds like tuning in on YouTube. If you want to come and play on the Twitch side, we have a slightly more active chat, but you are welcome to tune in from wherever you are watching. Okay, cool. So we are at 7 minutes after the hour. We started a little bit late, but that is all good. So let me just clean up my desktop for a second, and we will get going. So if you did not tune in last time, really all you missed was an introduction to Python. And so if you have sort of a basic understanding of Python, you are more than set to jump in with us today, where we start playing with pixels. So let's see. Let's just jump over to the punch in. Okay. So we'll have everybody go to collab.research.google.com like always. I will drop that link in the chat. And we can just make a new notebook. We don't need any of the code that we wrote last time. Also, let me see if I can fix my, this is the thing, is every time I restart OBS, it forgets all of my, cameras. Okay, there we go. There I am. Okay, sweet. So we have a new blank collab. We can call it something like playing with pixels. Because there we're just going to look at images and image data. And when we talk about like what is an image, what do we mean by that, right? So I'm going to pull from a concept that we talked about last time, which is lists, right? So you can do a list. You can say my list, and you can put in, the numbers 1 through 4, easy. And if you say my list, boom, you get your list back. This first cell that you run will always take a second to start up, but no worries. Cool, we have my list. And one thing that we touched on, but we didn't dive deep on, is the fact that you can put anything inside a list, right? You can put numbers, you can put strings, and you can even put other lists, right? So I could even make a list that was, a list of lists, and we could do 1, 2, 3, 4. Oh, I got really bright all of a sudden. What is up with that? Maybe I'll be less bright. Pardon me. Way too addicted to the lighting aesthetic, Okay, maybe that's fine. Cool. So we can make a list of lists, and functionally, and this is why I formatted it this way, is you can see that we basically have a grid, right? And we can print my grid. We could print it normally like this. In fact, let's call this, instead of my list, let's call it my grid. And we could print it like this, but we could get fancy and say print, and then star, and then sep equals new line. And this would give us a slightly cuter graph, or slightly cuter grid. The fun little syntactic sugar here is this star just says, basically take all the things inside this list and pass them as separate arguments. And the sep argument just says separate all of those with a new line. Yes, we are going fancy. A lot of times I try to make things really accessible, but I feel like every once in a while I have to pull out my Python syntactic sugar just to prove that I know it. So fun way of printing out a list on multiple lines pretty succinctly. And we have our grid, right? We can also, last time we talked about importing libraries. So I want us to import matplotlib, just like we did last time. So we'll say import matplotlib.pyplot as plt. This is a line that after you've typed it enough times, you just start, you just kind of memorize it. But if you need to, copy it down from my screen, you can. Also, like we did last time, I'm just going to, let's see, share. Anyone with the link can view. Let's copy that link. So if you want to actually pop in here and look at the code as I'm writing it in a separate screen and copy and paste, you are more than welcome to do that. My feelings will not be hurt. So we're importing matplotlib, and one fun tool that it gives us is this function called imshow. Now, imshow really takes any two-dimensional thing. So we have a two-dimensional grid up here, a list of lists, and we can throw that into imshow. And what this is going to do is it is actually going to render our two-dimensional list as an image. And boom, looky there. Okay, cool. Hopefully this is feeling fun, actually, because we just made some pixels appear, right? And I kind of just wanted to jump in and show you this, but ultimately that is what an image is. An image is a two-dimensional array of numbers, right? And we can go into a lot more depth on how we store images and how we encode them and how do you know what color it is and all this stuff. But that is like the big reveal is when we're talking about image data, we're really just talking about a two-dimensional grid of numbers. Now, one question you might be wondering, or you might be asking, yes, we made an image, and it's kind of cute, actually. One question you might be asking, as I gesture to this very fun-looking graphic, too late for pride, and that's not even a pride flag, is where do these colors come from, right? We said 1, 2, 3, 4 as our actual numbers up here, but we're getting like oh, actually, this is the time that I confess something. I'm actually colorblind, so I was about to say these are what the colors are. If I was going to guess, I would say we have like a dark blue, a medium blue, a green, and like a yellow. Those are the colors that I would say they are, but don't at me because they might be wrong. But basically, Matplotlib just picked some random colors for us. And it promises us that all the high numbers are going to be similar and all the low numbers are going to be similar. But it doesn't, at this point, it's not letting us control the colors. And you might say, well, hey, what if I want to control the colors? And that is where we can get a little bit fancier with our image data. So let's add another cell. Oh, also, I kind of skipped this house. What do you call it? Housekeeping? Yeah, housekeeping. I kind of skipped this housekeeping. If I am talking too fast, please tell me, hey, you're talking really fast. Can you slow down? If you have any questions, please type them in the chat and I will look over every couple of minutes and hopefully respond. And if at any moment you feel like I'm exhausted, you are more than welcome to just hang out with us and you do not need to code along. It's been a few minutes, so I'm going to drop this link again. If you want to jump in and join us, you can come to colab.research.com. Okay, so somebody asked, where did the y-axis values come from? Yeah, that is also a great question. Oh yeah, that's so interesting. And I actually don't have a great answer for. Well, okay, so I have an answer for you. So the main one is so we start with cells, right? And it is rendering it sort of like top down and left to right. And so what you're getting is this first cell. If we actually drew borders, you could see it. This first cell is the 0th cell. And so, okay, we put a 0 index right there. But because it has like a non-zero height, it does end up saying, oh, well, it extends all the way up to -0.5 and down to 0.5, right? So it flips our y-axis just because we often think of starting counting the image from the top left, because that's like the order in which we put in the lists. But so if you kind of flip it around, you can see, okay, well, you do have 0, 1, 2, and 3. Why it is rendering them as floats and giving us the 0.0 or the 0.5, I have no clue about that. But yeah, it is giving us the index of our lists. So we have our 4 rows here. And so, okay, this is 0, 0, and it ends up being right here. I guess we could actually go into that. So we have a two-dimensional list. And we talked about indexing things, right? And before, if we had a single list, if I go back and make my list with 1, 2, 3, 4, and if I want to get the third thing out, I will actually say, because we start counting from 0, I'll say this is 0, this is 1, and this is 2. And so I'll type 2 inside these square brackets, right? That's easy. We start counting from 0, and it goes up to 3, right? If we want to get into a two-dimensional space, we have to actually access both sort of the row and the column. So we could think about, first you count down which list you want to use. So this would be the 0th list, and the first list, and the second list, and the third list. And then you say, what column in that list do you actually want to use? So to be explicit here, we could say my grid, and if we say my grid 2, okay, it'll give us a list. But then if we say my grid 2 and then 1, we get a single number out of it. And right now, this number kind of represents our pixel, right? So maybe something that we'll do just to make it a little bit more obvious is I will, in real time here, give us a little bit more of a gradient. So instead of going just left to right, it'll go kind of swooping down. Is this Photoshop? Cool. And so if we render that, you can see it kind of fades from left to right. Oh, I missed one. Okay, yeah, this should be 6. And so now if we access that, we get, okay, it will be the 2 index list. So the second or the index 2 row. So we can go 0, 1, 2, and the index, what was it? 1 column. And so that's the index 1 column. And so we end up getting a 4. And if you render that, if we render that again, you can see we go from very dark, which is our low numbers, to very light, which is our bright numbers. Yeah, it's kind of fun how quickly you can make some kind of compelling looking art doing just messing around with our lists, right? I come back to this. Oh, why did it pick those colors? And the answer is Matplotlib has some defaults because we often give it data and we just say, hey, turn this into an image. And it has to figure it out. So it has some defaults set in for figuring out just some random colors to use. But if we want to be explicit, if we want to be specific and tell Matplotlib, these are the colors that I want to use, we can just get a little bit deeper into our image encoding. And instead of just using a single number, we can use 3 numbers. Now, before we get into this, which maybe you have heard the term RGB, or red, green, blue, we are going to look at technically a new data type, which is tuples. So we could say, oh, we want a black, and we will say 0, 0, 0. Now, this looks like a list, and in almost every way, it is a list. We are just using parentheses around it. And pop quiz, does anybody know the one big difference between a list and a tuple? Drop it in the comments, and if you're right, I will say you are very smart. And don't Google that, I can tell. Yes, Polar Void, you got it. Yes, Amit, you got it as well. So the tuples are immutable. Once you create a tuple, you cannot change it. And if you are really interested in why that is actually useful, ask me at the end, and I will like rant for like 12 years on why tuples being immutable is really, really important. But yes, we've got very, okay. And I'll do what I promised. Polar Void, you are very smart. Amit, you are very smart. Fancy Appleby, you are very smart. Yadav, you are very smart. Yes, we go on lots of side rants here. Welcome to Local Hack Day. Local Hack Week, Global Hack Week. Oh, we changed the name. I keep calling it Local Hack Day. Cool. So this is a tuple. And we're creating a variable called black that holds a tuple. Is it Hario? Hario, you are very smart. And anybody can get on this. Just type tuples are immutable in the chat, and I will be forced to live on stream say you're very smart. Limited time offer, folks. So we have this variable called black, and we're storing this tuple with 3 zeros in it. And what these represent are our 3 main color channels, which are red, green, and blue. So if I come up here and type a little comment, I can put an R, and then a G, and then a B. So this is how much red do we want in our pixel, how much green do we want in our pixel, and how much blue do we want in our pixel. And I could also make one called white, and we could say 255, 255, 255. Except now I have to fix the spacing so it all lines up, because I'm very invested in this. Okay, cool. And so generally speaking, an encoding you will see really often is 0 is black and 255 is white, or like the most color, right? And we could, now I'm actually kind of like interested in doing like a total derailing of this session and just getting into color theory and like, oh, what happens when you mix green and blue light? Which I don't know, maybe we'll do that. But yes, these are 0 to 255 ranged colors. Fun fact is you can actually use, IMShow will support 0 to their integers. It'll also support 0 to 1. Black is going to be 0, 0, 0, and white will be 255, 255, 255. And so what if I just said plt.imshow, Maybe now. Maybe now. Are we maybe hopefully back? Okay, cool. So fun fact, usually a pretty good bet that it's OBS. This time it was actually StreamYard. For those of you who don't know, StreamYard is the software we use to split the stream up across the internet, so it goes to Twitch and to all the other places. And yeah, it, for whatever reason, decided that instead of using my camera's audio, it wanted to use my MacBook's audio. But I missed you so much. I'm glad that I'm back. Yeah, it's good to see you again. Okay, so we get our first column is white and our second column is black, and it's a single row with 2 pixels, right? And this is exactly what we told it to do. So we have constructed another image, and this time we used an RGB encoding to sort of specifically tell Python this is, or to tell matplotlib, these are the colors that we want to use, right? But black and white, I mean, they're cool, but they're kind of limiting, right? So let's make some new pigments to use, right? Sorry, not pigments, some new lights to use. So we can call a red. And remember I said that the first column is red. So what if we said 255, 0, and 0? And we could do green, and we could say 0, 255, 0. So in this case, we're saying no red, a bunch of green, and no blue. And then finally, our blue, we could say 0, 0, 255. And so now what if we said PLT IM show, put a little list in there, and here we can get a little bit more exciting. We can go red, green, and then on another row we can say blue, white. Run this, boom, cool. We controlled some. Oh my goodness, I am so sorry. Yes, thank you for calling me out because I always forget to switch back. Yeah, no, this is the problem is I don't stream regularly. It's like, I'll go like 2 months without streaming at all. But hopefully the screen share is back. And this is what I typed out, is we made a little red and a green and a blue, and then we just created that image. So hopefully the screen sharing is now getting fully pushed back to you. And so I'm kind of, I feel like I'm feeding the fed horse here, but in our upper left column we have red, in our upper right column we have green, in our bottom left column we have blue, and in our bottom right column we have white. Let's look at what combo is the Microsoft logo. We got what, red, green, blue, and then what's that last color? It looks like orange to me. I don't know. It's somebody who can see colors to let me know in the comments. But yeah, I feel like we're pretty close. Let's say Microsoft bottom left. And let's see. Wait, bottom right. The bottom right is yellow? Okay. Well, let's see. Is yellow I feel like is green and blue, right? If we do 255 and 255, maybe. Let's see. That's not really green. I guess let's make it a little bit. So 255 is like fully bright. If we make it, that actually is not bad. That looks kind of. Oh wait, no, we're trying to make yellow, aren't we? Okay, red and green to make yellow. Let's try red and green. We're doing it live, folks. We're doing it live. Okay, that looks kind of yellowy. But now I want to make the green a little bit darker. What if we do like, just like 200 for the green. Okay, I feel pretty good about it. I think that we're officially ready to get sued by Microsoft. Also, if lawyers are listening, I'm sorry, I didn't mean it. Please don't sue me. Cool. So we can play with colors. We can build up images, right? And ultimately, that is all image data is. It is a 2D grid of RGB values. And walking through this whole bit, it's not strictly necessary to do machine learning with images, but I think it's really, really valuable to understand this is when you give an image to an algorithm, this is what it's looking at, right? And if you want to mess around with it in a way to help your algorithm, this is the kind of data that you are going to mess around with. And actually over the rest of today and then into tomorrow, we are actually going to build our own kind of dumb machine learning algorithm, just purely messing with the pixels ourselves. Okay, so another thing that I should warn you about is usually I like to have everything happen live on these streams, but because of the nature of like specifically training large image models, that's not always going to be possible. So I am for a couple of key moments going to do that thing they do on baking shows where they're like, put it into the oven, and then like 2 seconds later they're like, we have this other cake that we started baking 2 hours ago. So I am going to do the little cake swap a few times, and the first time that I'm going to do that is just by copying and pasting this relatively large list that I didn't want to make in real time. So here we have a 7x7 grid of our little pixels that we made in the shape of a heart. So if I just go show heart down here, boom, you can see a very cute little heart. And I wanted to get like an actual real picture. And I want to do a couple different things with this. I want to play around with it. So the first thing that I want to do is get the most common color in this image. Okay. Now, you might just be able to look at it and say that it's red, but of course that doesn't work when we're trying to build things onto algorithms, right? We need to actually explain in Python, how would you figure out what is the most common pixel here, or the most common color here? And there are a couple different ways you could do this, but here is a relatively fast, straightforward way that we're going to do it. Oh yeah, drop some hearts in the chat, y'all. Oof, okay. So we're just going to create a list for all of our pixels, and we're going to create it empty. And we're going to say for row in heart. So remember, this is a for loop where we're just saying, because our heart is really just a list of lists, every element inside our heart is a row, right? So we'll say for row in heart. And we could even just, for a first step, just print out the rows. Okay, so that's like a lot of data, kind of a hassle, but you can see each of these is a row, and each row is a list of pixels, right? So now we could say for pixel in row. Okay, and now we can print out each pixel if we wanted to. It's going to get really messy. Okay, so lots of pixels. But now what we're going to do is we're just going to say pixels.append pixel. So we get a list of all of our pixels. Another kind of simple way you can think about this is that our original grid is two-dimensional, and we're just flattening it into a one-dimensional list of all of our pixels. Now we can use a super fun, hot, sexy tool from the collections library. So we can say from collections import counter. And actually, before I use it on this, I just want to show you how counter works. So we can call counter on a list of anything. So we could do it on a list of numbers. There's a bunch of random numbers, and we can store that in a variable. So C is now a counter object. And we could say C.mostCommon. And in here, we can actually pass an n variable. So we can say, oh, give me the 3 most common things, right? And this gives us the 3 most common numbers. So the most common number was 2, and it happened 4 times. The second most common number was 3, and it happened 3 times. And the least common number was 4, and it happened 2 times. There's some nice kind of some symmetry there. But so the counter just counts up how many times it sees each of the things, and you can ask it, what are the most common things? That's what counter is. Somebody asked, can we flatten it with syntactic sugar? And you could, let's see, how would you do that? Could you do a list? You couldn't do a list comprehension. You could do a generator comprehension, I guess, and yield all of the things unpacked. I'm actually curious, Polar Void, what would be your one-line syntactic sugar to unnest a 2D array? I'm sure it's not actually that hard. Okay, we're on a side tangent. Let's see, flatten 2D list Python syntactic sugar. I'm not gonna, they keep being like, oh, import this library. I'm not gonna import a library. That's not the point. Oh, right, you can do the 2 list comprehensions. Okay. This is something, I do like whipping out some some fun syntactic sugar. I think the list comprehensions, I just have decided that I'm not gonna get into this time, but it can be done. I digress. So we're going to use our counter object to just say counter, and then count. We're going to pass in all of our pixels. So this will say pixel counter. We'll call it that. And so down here we can say pixel counter, and we can just say most common. If you don't pass anything in, it will just give you all of the things in order. So here we can see our most common thing is this guy, and our second most common thing is this guy. So we have 27 pixels that are red, and we have 22 pixels that are white. And so we could even come in and, if we wanted to, we could say, let's see, most common. We'll look at the most common color. And so this is actually because the thing in the thing in the 0th index is technically a tuple, and the first thing in the tuple is another tuple, and the second thing in the tuple is the count. We are unpacking the tuple into most common color and count. So this is, I will say, this is like the kind of thing that gets a little bit complicated, is just when you have data nested inside other data. And so if that ever gets a little bit murky, don't worry about it. We will. Oh, I just noticed all the hearts in the chat. Thank you for the hearts, y'all. If nesting data inside other data is ever like complicated, just ask a question and I can walk back through it. But so we have a list that has two tuples inside. One tuple is this guy right here, and then another tuple is this puppy. And the first tuple, actually both of them, are tuples of both a tuple and a number. So inside the tuple, the first thing is another tuple, and the second thing is the count of how many times that tuple appeared in our image. Let's see, somebody asked, am I too late? How much you teach? I miss every, or what? So we haven't gone super deep. We have just been playing around with pixels and playing with image data, and I will drop the link if you want to follow along live. Oh yes, Fleabag, thank you for chiming in. I always appreciate it when folks answer other folks' questions. But you can jump in and join us if you want to. You can also just go to colab.research.google.com, Google, and you can sort of follow along live. Okay, so we got our most common color. And if we wanted to, we could pull that most common color out and say plt im show. And if we want to actually render this as an image, we actually have to just double nest it inside lists, right? But this will give us a single pixel that is the red, right? Hopefully we feel okay about that. Okay, so another thing that I want to look at is, what if instead of getting the most common colors, what if we got the average color of all of the pixels? So we're going to write another for loop, but before we do that, we're going to create some lists. So we're just going to pull out all of our red values and put them in a list, and all of our green values and put those in another list, and then all of our blue values and put those in a third list. And I will say for row in heart again, so this goes row by row for all of our pixels. And then we'll say for pixel in row. So this will go column by column through our row. And so then we can just say red values dot append pixel, and we're pulling out the first thing, or the 0 index inside that. And we can just copy and paste. And so then we can say green values, and we're pulling out the second value, right? And that'll get us our value for green. And then we can put a 2 there, and that will get us our third value, or our blue value. So we have now just gathered up all of the reds and the greens and the blues. And so now we can, from NumPy, import NumPy as NP. So NumPy is just a math library that includes a lot of fun math functions, including a mean. So we could say our average red color is, we can just say NP mean of our red values. I can type, trust me, I can type. And then we could say average green is equal to NP mean of our green values. Hopefully this does not feel super complex. And then finally, our average blue is NP mean average blue. Oh wait, blue values. Cool. And we could just print all these out if we just wanted to see, or we could really say our average color is all of those average values stitched back together, right? So we'd say average red in the first place, average green in the second, and average blue in the third. So just to recap, what we're doing here is we're averaging all of our reds together. So it's how much red is in the first pixel, how much red is in the second pixel. And then we're averaging all of our green values, and then we're averaging all of our blue values. And then we can put them back together into sort of our average composite pixel. So if we ran this, and we just say average color, okay, you see some pretty long numbers. And something that we're actually going to want to do is turn these back into integers. Because when we run IMShow, if it's not an integer, it's not going to expect it to be on a 0 to 255 scale. So we can turn all of these values back into integers just by wrapping our average call or our mean call in the int constructor. So the int constructor just says, take whatever is inside here and turn it into an integer, right? Awesome. So now we have an average color that is 255, 114, 114. And what if we wanted to see what this looks like? Well, we could say IMShow, and just like before, we could do double brackets. So we have a list inside a list, and we could just say average color. Oh, not IMShow, plt.imshow. And boom, we get this kind of dark pink, right? Or medium pink. I don't know. I'm still colorblind. But if you scroll back up to our heart, and if you just squint at it, and try to make it all fuzzy, like, yeah, it's like approximately that color, right? If you kind of average all the pixels together, it kind of looks pink. Yeah, we did do a little bit of, I'm going to call it a parody work because I think that's legally defensible, but we recreated the bootleg Microsoft logo. Oh, somebody said salmon. That's a fun $10 color. Yeah, it's kind of salmon. Awesome. Okay, so we've learned to play around with pixels a little bit. We know that an image is just a two-dimensional grid of RGB values. And we know that we can do things like find the most common color or find the average color in all of our pixels. And let me just see, where do I want us to head? We are 40 minutes in. Yeah, okay, we're actually going to dive into, we're going to pull some real data in. Get psyched. We're going to really mess it up with some data. So I have prepared a fun little data set for us to use, and we can pull it into our notebook here using a special kind of command. So if you ever start a command with an exclamation point, this basically tells Jupyter Notebook or Colab, I want you to run this command just in like in your shell. So it kind of runs it in the computer this thing is running on. And I have this command prepped over here where if we say git clone and then this URL, this is actually where I put all of the data for this project. We can pull it here locally. So I will drop this command in the chat so people can just use it. And I'll kick that off. And we will also go actually to the GitHub repo. So if you come into art, it's pretty bare bones. But if you come into art, you can see we have, this is pretty small, isn't it? We have a list of artists. Some of these you might not be familiar with. Albrecht Dürer, actually, warning, we're going to go on a tangent. So Albrecht Dürer was a printmaker, I want to say in like the 800s, like really old. Maybe it was later than that. Maybe it was like the thousands or something. But, okay. Really going on a little tangent here. In college, I did a bunch of different majors in college, but one of them, I took a lithography class. I started as a mechanical engineering major, and then I briefly was pre-med, and then I was computer science, and then I did this like make your own major, and it was like philosophy and AI. Lots of fun. But in between there, we crammed a lithography class. And if you're not familiar, lithography is it's this practice of printmaking where you get a giant chunk of rock and you put a bunch of like oil on it, and then you sear that oil with acid, and the parts that have oil on them are like protected, but the parts that are not protected with oil get seared away. And so you end up actually burning away a little bit of the stone, and that oily part, it stays, how would you say, like oleophilic, like it wants to draw oil into it. And so then you can use oil-based pigments. And my first, I hope you can still hear me, but the first large project I did, which I will see if I can find it. Oh, there we go. It was, boom. This is actually a reproduction of Albrecht Dürer's praying hands. And there are some hands, and they're praying, and that's the whole art project. And then you can do a thing where after printing, you mess around with it, and you print something else. And so for my something else, where are you? Okay, yes, so for my something else, we messed up the image, and I don't know if the light's going to cooperate. We put the praying hands in handcuffs and then put a little bunch of speech bubbles all around it. And that is my exposure to Albrecht Dürer. Anyway, we have a bunch of artists. That was the whole tangent. Oh, thank you. Oh, thank you. Yes, thank you for playing along in this walk down memory lane. I love the praying hands were right there. So Albrecht Dürer made the praying hands. And Andy Warhol did a bunch of these sort of pop art kind of things. You can click in and you will have a bunch of individual images. If number one isn't the praying hands, I'm gonna lose my mind. Okay, number one is not praying hands, but this is apparently another piece of art by Albrecht Dürer. Okay, the second one that I randomly clicked on is also not the praying hands. Hi, Farhan, welcome. Okay, but yeah, if just for completeness, Albrecht Dürer praying hands. Boom, there's the original. I think mine looks fine. I think it looks good, yeah. I'm pleased with it. So this is the data that we have just downloaded. And if you come back into Colab, you will see it ran some code. And if you come over here, you will see we now have this new file that is Global Hack Week 2022 09. And if you click in, you see we have those same files. So we just pulled a bunch of files down from GitHub, and we will play around with them. So the first thing that I want us to do is I want us to actually import another library called OS. So OS just gives you a lot of tools to mess around with your operating system. It can do things like create files and open files and list files. It does a lot of stuff with files. You can also do a lot of other things, but OS just lets Python talk to your operating system and ask questions about the files you got. So the first most basic thing I want us to do is a command called os.listdir. And we can actually just copy this right here and put that inside some quote marks. And this will show us all of the files inside of GHW 2022-09. And if we want to go deeper, we can come inside this string and put, let's see, art. Yeah, art's the one we want. And we will see all of our artists. Now, you may wonder, hey, couldn't we just look at these in like a file browser? And the answer is like, yeah, we could. But this actually gives us a list of all of our artists. Oh yeah, my favorite artist, .ds store. But it gives us a list of all of our artists that we're going to mess around with in the future. You know what this is called, kids? This is called make yourself a .git ignore. You will thank yourself for it later. True Git fans will understand. So we can now even go further into our directory structure, and we can grab, let's say, Vincent van Gogh. I almost said Vincent van Gogh like I was a Brit, but I could never. Okay, cool. So we just have a bunch of lists of individual images. And to play around, why don't we just take this one at random? Oh wait, I didn't mean to actually run that. It's not a directory. We can take, okay, we'll take this image. We will scroll all the way down
into our new code cell. And let's grab this path. So we have just navigated around inside of our directory structure and looked at all of the files that we have. And we have just rebuilt up. Here is a path to an individual image. And so, okay, what if we want to actually see what this image is? And pardon me while I scroll vigorously off screen. And we're going to use another matplotlib little utility, which is plt.imread. So imread will just go to this file and say, hey, give me the data from this file, which is an image. So we could say Van Gogh image as our thing there. And so then from here, we can just say plt imshow and pass image into it. So now if we run, we see, wow, it's a Van Gogh, incredible. And we can see the image. And you can see it has way more pixels than the ones we've been playing around with. So it has 800 rows of pixels, and it has 1,000 columns of pixels. So what is that? Is that 800,000? Is that how math works out? Yeah, I think it is. So we have 800,000 pixels. But bring us back. What is this actual image thing that we just uploaded or just read in from the file? If you hit return, you will see, just like we've been talking about, it is a two-dimensional array of RGB values, right? Yeah, it's just a bunch of pixels. And that is like a good thing to remember, that even when we were looking at an actual picture of a painting, it is just a bunch of pixels. And that means that we can do a bunch of the things that we were doing before. Like, for example, we could ask, well, what is the most common color? What are the most common colors in this image? And so in order to play around a little bit more effectively at scale, I want us to actually write a function. So the first function that we're going to write is we're going to say most common colors. And this is going to accept an image, and maybe we can optionally accept a number, but by default, we'll just return the 3 most common colors. Let's see. Yes, yeah, Polaroid is right. DS storage it's a Mac OS thing that stores some metadata. I think one of the things it stores is what the icon will render like. Let's see. Okay, so we've created a function called most common colors, and it's going to accept an image and an n, which is how many common colors it wants us to return. So this is just the header for our function. Remember, a function is like a recipe that you can use again and again. And so what we'll do in here is we will actually just scroll all the way back up and copy our most common colors code from, we did that first, didn't we? Yes, from here. And we can scroll all the way back down and just paste it in our function. Now we'll have to fix the indentation, so you can just copy all of it and hit tab, and that'll tab it all over. Also, we don't want to be looping through heart anymore. We can just loop through image. We don't necessarily need to import collections again, so we can delete that. And we'll have our pixel counter. So this is doing the exact same thing. The only thing we need to alter here is we just want to return the the n actual pixels that are the most common colors. So we could say pixel counter dot most common, and we could pass n equals n. So this is basically saying whatever n value we got, we'll also give that to our counter. And we could say most common color tuples. Okay, so remember, we could even just print most common color tuples just to check in with what our work is doing right now. So what would happen if we actually just passed the Van Gogh image to most common colors? Oh, incredible. Okay, we have the issue of an unhashable type, which is actually gets me into why tuples are so cool, which which we might have to talk about anyway. But maybe, what can we do? Can we do image dot value? Maybe we just turn, let's see. Maybe, yeah, what if we just literally turned this into a tuple? Would it let us? Oh, it will let us. Okay. So, seldom playing. No worries. Welcome to the party. You are welcome to play along with us. I will share the link again if you want to actually see my code as I'm writing it. It's good to have you here. Basically, all we've covered so far is we have looked at playing with pixels. We've talked about this idea that all an image is an array of RGB values. And so then we just pulled in our data from GitHub, which I can drop the link for that again. You can also pull all of these lines of code out of the collab if you want, because they're there for you. But so what we did is our image started as, you can see that down here, I said it was a 2D grid, which is true, but it is wrapped in this thing that says array. And an array is kind of a, for Python people, I would say it's a special kind of list. But for people who are not from Python, this is kind of your classic sort of like C++ style array of like, this is just a chunk of memory with a bunch of data in it, right? And we don't do any fancy things for you. This is just a bunch of memory, and it's very efficient and it's very sort of good for performance. But one thing that it also is it is mutable. If you want to, you can change something in the middle of it, right? And oftentimes this is really nice because you want to mess around with your data, right? But in some cases it is not useful. And because we're about at an hour, and we'll try to get through a little bit more before we log off. So I'm not going to go too deep into this rabbit hole, but suffice it to say that anything that uses a underlying it, when it uses something like a dictionary or a set, which Counter does, you cannot put anything in it that is mutable. And the sort of very short reason I would give is this is like in a dictionary where you have your keys and your values. And so your key has to be immutable. And the reason for this is, well, think about a dictionary like a bunch of boxes on your shelves, and you put labels on your boxes, right? And you can change what's inside the box, right? Maybe I have a box labeled fruit, and I put an orange in, and then I put a banana in, and then I take the orange out, and like, hey, it's still a box of fruit. But if I put an orange in because it says fruit, and then somebody else comes along and changes it and says, hey, this is now race cars in this box, it would mess up the whole conceit of having boxes with labels. The truth is a lot more about hashing and running time complexity and a lot of other things. But the short version is you need something that is immutable if you're going to use it as a label for another thing. And that's what Counter does. Hopefully that was not too deep of a rant. But that is why right here, I took our individual pixel and just turned it into a tuple, in the same way that we turned things into ints like earlier. Okay, so I know this is like a decent chunk of code here, our most common colors function, but we're not even done. So we printed out our most common colors, but we actually still printed them in that Counter dictionary, the tuples of, okay, this is the color, but then this is how often it occurred. And we don't even really need that, right? So let's actually loop through, I will go into list comprehensions. So something I could do is I could loop through, and I could actually say most common colors and make that an empty list. And then I could say for most common color and count in most common color tuples. So this is saying loop through this list of pixel count tuples and unpack them into most common color and count. And so then I could just say most common colors append most common color. So this is just going through and pulling each of the actual pixels out of the pair of pixels and counts. Hopefully that isn't too crazy for anybody. And so then we could actually just take most common colors, and we could even return most common colors. And this is fine. It'll take a second to run, but we get this that looks kind of like a lightish color, another lightish color. Three fairly light colors. Interesting. And this is our list of most common colors. But we can get even more succinct. So there's this thing called a list comprehension, and it is just a fancy way of writing a for loop in this exact pattern. So turns out a really common thing we do in Python is you loop through a list and you change it a little bit and you put everything back into another list, right? So that's what we're doing here is we're looping through our tuples, we're picking out part of it, and we're putting all of those back into another list. But Python gives us a really, really short and I would say elegant way of writing this whole for loop. So what we can do is we can just, I'll sort of in real time unpack this into my list comprehension. So we can say for most common color and then comma count in most common color tuples. And then before all of this, we write what we actually want to go into the list. So in this case, the thing we're actually adding back into our list is just most common color. And now we can actually delete this whole line, and we have our list being created in a single line of code in a way that feels kind of fun. So we can run this again, and boom. Okay, we get. I think these are I don't think they are the exact same numbers, right? Are the exact same pixels. And so now, if we wanted to, even we could say plt imshow, and we could pass in just wrapped in one more list. We could pass in our images, and okay. So this is actually great. So you will see basically all of these are white, right? Somebody mentioned list comprehensions. Oh yeah, I've said list comprehensions are cool but scary. Yes, they are. And I will say, I think sometimes. Oh, pardon me, I'm gonna sneeze. This sneeze escaped me. I will say I think that list comprehensions are often used more than they need to be. In fact, in this case, just because my variable names are rather long, I don't even know if this is like the right thing to use here. I would say that when in doubt, you can just write yourself a for loop and you're just fine. But something you'll notice is that all three of our colors are like really light. And so if we scroll back up, we can come and look at it and okay, why is that? Well, the answer here is, at least the answer that I would guess is the case, is that there are like a gajillion colors in here, right? We have a bunch of different shades of a bunch of different colors. And if you think about it, because each color is uniquely defined by a tuple of 3 numbers from 0 to 255, well, what is 255 to the power of cubed? It's this. So this is the total number of colors we have in an image, RGB encoded with 0 to 255 granularity. That's a lot of colors. And so what you end up getting here is not really anything super meaningful, right? Because it's just like, well, in the shading, like what color happened to appear slightly more. But this doesn't really capture any of the colors that we really see, right? And so we're going to do something to fix this. Bear with me. I think this will be like the last big project we do today, but we are going to do something to more effectively pull out the most common colors from this image. And that is something called posterization. Okay, I'm going to drop a link in the chat. This is just the, okay, we're going to pull back up Colab. Let's see, playing with pixels. Actually, I'm not going to drop any link. I'm just going to Google posterization, Wikipedia. Okay. Is it go or go? That is a good question. Oh, y'all are just so good at getting me running down little tangents. We have. So I wrote G-O-U-G-H. Am I? Oh no, I think you're totally right. It is just G-O-G-H. Yeah, thank you for the catch. Van Gogh. Oh, we scroll for fun. And go. Okay, posterization. So this image of Sneck, I think, is a really good one for showing posterization. And what posterization does is instead of having sort of the gradual transition of colors from one color to another, it chops it up into blocks. And it says, okay, you're either going to be this color or you're going to be that color, and there's no in between. And you can see, oh, hey, this already looks, like pretty good. Sorry, this looks pretty good. Not as good as the original image, but you can still tell that it's a snake. In the caption here, it says, example of photograph in Jpeg, 16 million colors, and after, only 256 colors. Cool. So that is posterization. And we are going to implement our own posterization algorithm, because once we do that, if we get the most common colors, you can see there are just a lot fewer colors in here. And so the most common colors are actually going to be more meaningful, as opposed to just being sort of a random statistical anomaly, right? So we're going to continue on our path of just playing with pixels, and we're going to implement our own posterization algorithm. Okay, let's plop in another code block right here. So we're gonna create a function called posterize, and it's going to accept an image, right? But the thing that it's going to return is just going to be another image. So at the very beginning, we'll define a new image, and we'll just create it, set it equal to an empty list. They used to make me believe I have reduced atomic complexity. Yeah, that's actually really. So another little side tangent. So I interview at Google, right? I didn't actually give myself a formal introduction. I think most of the people on stream like know me. My name is Will. I'm a software engineer at Google. I'm also a coach at Major League Hacking. I'm a Python enthusiast, and I'm very caffeinated. That is my intro. But at Google, I do interviewing, and it is like a really common thing that folks will come in and they will write something on a single line of code, and they will think that means that it's constant time, right? Because it's a single line of code. There's no for loop involved. And it is tricky. So yeah, and I think that solid playing, it's a good point, and maybe a good reason to not use list comprehensions if it's going to trip you up like that. Polar Void asked if there's a coffee stream this week. There's not actually. Yeah, it was originally not scheduled, and then we thought about scheduling it, but I realized this week is going to be busy for me. So I'm very sorry. But next time we will do a big espresso, Hack Your Espresso event. Okay, back to the actual coding for a second. So we're accepting an image, and we're going to be creating a new image. And the way we're going to create this new image is basically by just chopping off part of our number, right? So right now our numbers go from 0 to 255. And what if we just chopped off you could think about chopping off the 0 digit, the ones digit, or you could even chop off the ones and the tens digit. And so I'm going to actually do a little explanation of this. So say we have a number, right? Say our number is 255. So if I want to get rid of this first digit, this would just turn into 250, right? And we'll call that a comment. And so one of the ways that I can do this is I can divide it by 10, and then turn this resulting number into an integer, and then multiply it by 10 again. You can see this turns 255 into 250. You can up this, and you can do it with 100, and it would just turn into 200, right? So really what this is doing is it's combining a bunch of different numbers into the same number, right? So in this case, we could do 245, or we could do 201, and all of these will turn into 200. If, on the other hand, if we did 155, this turns into 100, right? Exactly. So this lets us control the granularity and group a bunch of colors together, right? So when we go into posterize, why don't we even start by defining a function that is, let's call this function posterize pixel. So this will accept a pixel, and we're going to return a new pixel. But we're going to create this pixel by posterizing or by controlling the granularity of all of the individual values. So let's say our new red value is going to be equal to, so the first thing in there will be our red value, and we can divide that by, for starters, let's try 100. So we can say, we'll turn all of that into an int, and we'll multiply it by 100. So this is just going to say, if you have a lot of red, you'll be 200. If you have a medium amount of red, you'll be 100. And if you have no red, you'll be 0, right? Those are like the 3 bins that it will push us into. Okay, somebody's asking about integer division. And yes, I think in this case, you could use integer division. It just saves you the having to call int on it. So long-time Python fans will know that if you put a second slash in there, it basically forces the result to be an integer, and it will lop off the ending part. And in fact, I think there's a case to be made that's even more elegant. We've already used the int. I'm always conscious about introducing new concepts, and we technically covered the int constructor and didn't cover integer division, but I think it's a cool enough one to actually throw it in there. So we could say integer divide by 100, so that'll throw away the fractional part, and then just multiply it by 100 again, so it's still kind of like the same number there, right? And we can do this for all of our values. So we can say our new green value, we'll take the green, and we'll just type out new green value. And then we'll do our blue value, which will be index 2, and we'll say new blue value. And so then we can just return a pixel that is new red value, new green value, and new blue value. And so I want to, let's give this its own cell block, actually, or its own code block. Okay, so I'm going to run that. And now I want to actually just test it out on some example pixels. So we could say posterize pixel, and we could say, let's say red and green are medium, and blue is 0. Actually, sorry, let's give really interesting colors here. And blue will be 3. And when we posterize this, it just chops it down to 100, 100, and 0. And so it makes it a much simpler thing. And if you think about it, because now our only values are 0, 100, or 200, our total number of colors is just 3 times 3 times 3. So what is that, 27? So now we have 27 possible colors that we could use because we're forcing all of our colors into these very specific boxes. So we could posterize a pixel, and our posterized image will just be us posterizing all of the pixels individually. So we can say for row in image, and then we can say for image in, for pixel in row, and we can say posterize pixel. And then at this point, we can actually create a new row. So for every row we go through, we'll create a new row. And then for every pixel in that, we'll posterize the pixel and append it to our new row. And then at the end of processing our whole row, we can say to our new image, append our new row. And at the very end, we can return new image. Awesome. So now I want us to take our original Van Gogh, and I want us to, here's what we'll do. We'll pull this down to a new block down here. So we'll show the Van Gogh image, and plt.show just forces it to actually show. And then we'll say plt im show our posterized Van Gogh image. In fact, actually, to make this clearer, I'll just call this posterized Van Gogh image. And we can show that. And, okay, we have a fun little bug. numpy.uint8 object is not iterable. Okay, what are we doing wrong? So we have our Van Gogh image, and our Van Gogh image is right. We just showed that. So we say for row in image, and then we just say for pixel in row. So what if we just print out our row? And if we run this again, so we're just debugging in real time. So we print out our row, and oh, do we want to cast this? So my sense is that possibly well, that doesn't make much sense. So our row is this thing, and it's saying that it's not iterable. And we're calling it on Van Gogh image. Yeah, we're going real deep. Okay, so I'm going to try turning our row just into a list. It's not going to be very performant, but I'm kind of curious to see if that helps at all. It's still saying for interesting. Posterize pixel. And it's saying that this row is not iterable. Yeah, we are going pretty deep, implementing our own posterizing algorithm. Like maybe I was a little bit unfair when I said this was like the same difficulty level as yesterday. But okay, so for row and image, we're printing our row. Maybe let's just try this on a very simple image. So what if we said posterize, and our image was just our heart? Okay, cool. We're getting somewhere. So this says int is not iterable. Okay, so we are somehow getting too deep into it. We're saying for row in image. And then we're saying int object is not iterable. So somehow row somehow row is giving us a oh wait, int object is not iterable. So this is telling me that whatever row is an integer at this point. But if we print out, the only thing we printed is row, and it looks like it's printing all of this and then this number. Okay. Just look at our heart again. Heart looks good. There's going to be something very simple that I'm missing here. No, as in it's a list of 3 RGB values. Image. Okay, I don't want to get too held up on this little thing here. For row in image. Okay, let's just back up for a second. I wonder if I had any kind of typo there. For row in image, print row. And we have, cool, we have our rows. For pixel in row, print pixel. Cool, these are all pixels. So now posterize pixel. Oh, that's super interesting. It is so that this is a thing that Python will do for you sometimes, is it will tell you that the error is on one line and the error will probably be or will possibly be in another. And it seems as though it is giving us some misdirection here, because just running that at first, when we're just printing it, it is fine. Row is only printing 255, not the list. Yeah, that's like kind of what it seems like, that somehow our like there is a row that just has 255 in it. And if we just posterize an individual pixel, that works. Is it possible that I have something overridden, like that I'm naming something else somewhere? For row in image, for pixel in row. Oh, oh my goodness. Yeah, Fleabag, you got it. You got it. No, it actually just dawned on me is that I am calling posterize on pixel, not posterize pixel on pixel. Yeah. Oh my goodness. How long did I spend just staring that in the face? Thank you so much, Fleabag. You are brilliant, and I appreciate it. Okay, so we were posterizing we were calling our image posterize function, which maybe we'll just rename that image posterize, or posterize image, just to make that clear. Where we really wanted to be posterizing our pixel. Okay, brilliant. Yes, we all had a collective moment there, and I thank you for bearing with me through it all. Okay, so here we will now say new. Okay, I'll add back in our new row. New row equals an empty list. And we can say new row append posterize our posterized pixel. And at the end of the row, we will say new image, and we'll append our new row. Okay, so now we posterize our heart. This actually means nothing to us. It is, all right, because we actually have to, well, one, we have to return our image, return new image, and we're not printing anything now, right? And so if we do im plt.imshow posterize heart. Oh wait, no, not posterize heart. Image posterize. This is the thing. You can give yourself really good function names, but you have to actually use them. Okay, cool. So this is our posterized heart. And I'm glad that we did this, because it kind of makes a few things clear. Is that we are actually messing with our image and destroying some of the information here, right? So like in this case, the red is not going to actually be as bright red, right? Because that's going to drop down to a 200. And in fact, on the flip side, the white, it now looks like is a little pink. Which that actually doesn't totally make sense to me. I would guess that it would all go down to white. Although I don't think that we necessarily need to spend time debugging that. But so we lose some information, but it's going to flatten it a little bit. So now I want to actually try our posterize image, come back down to our Van Gogh, and posterize image on our Van Gogh image, and that'll give us a posterized version of it. And one thing that you will notice is that the first image prints out very quickly, and the second one takes a minute. And that is for lots of reasons, but the biggest one is that our posterization algorithm, it takes a long time to run, right? So if we scroll down, we now see the same image, except now we only have 27 colors, right? Because each RGB value can be somewhere between basically 0, 100, or 200. And so 3 times 3 times 3 gives us 27. And so instead of sort of like all the variety in the original photo, it's kind of flattened, and we are getting kind of chunks of color. So now that we have posterized this image, I want us to again call most common colors on it. So we'll say most common colors not on the original image, but on the posterized Van Gogh image. And then I want to say this is posterized most common colors. And we'll run that. And then let's just say plt.imshow, and inside a list say posterized most common colors. And boom, these are the colors we get. And so if you scroll back up, you can see, okay, that's maybe not the most important or most common colors I would have picked necessarily, but they seem to kind of capture what's going on. There, we have some sort of gray-green tones that I definitely see, and we have that black that shows up a bit. But we could even say, instead of n equals 3, we could say n equals, I don't know, 10, and get the 10 most common colors. And so suddenly here you can see, okay, as like a palette of colors here, you can see quite a bit more variation. Another thing that we can play with is we cut off to just to like the nearest hundreds place, but there's a lot of places in between that you can cut off. So something we could do is, instead of cutting off to the hundreds place, something I might try is cutting off to the 64ths place, which is an even power of 2, and so our 255 will divide into it. Yeah, it's actually kind of impressive how good an image you can get with only 27 colors, right? Like, it still does kind of look like the image. I think Van Gogh's style actually helps us there because it is kind of, cacophonous. Okay, so question, how would you posterize an image without making it darker like we currently do? So this is a little bit of another rabbit hole. One thing that you can do is, so here we're kind of doing dumb posterization, but something that actual posterization algorithms will do is they will actually look at what colors do you actually have, and you will cluster them. And now I want to take like a whole separate day and just teaching you a clustering algorithm just so we can posterize our images better. But I know we can't. That's getting off topic. But so something you can do is basically you can just group colors together. And so say, okay, what if I want 3 color clusters? And so you'll actually just use another machine learning tool to basically draw your clusters of colors. And so you're kind of putting all your colors in 3 bins, and then take the average of each of those bins. And that gets you a lot of a sort of cleaner, the thing we're doing right now is really image independent. Now, something that you could think of if you just want to not make it darker, because right now we're like properly truncating it, right? We're only bringing things down. And so something that you could do is, because on average, things are going to go down by half of what you're truncating. Yes, I would use k-means. K-means would be my algorithm of choice. But so something that we could do is we could actually add back half of this thing that we're truncating. So we could, instead of just doing that, we could then add back 32. And you could do this to all of them. So this will be our new posterized pixel. We're going to posterize image. And if right here, oh, right, I was confused by the white. But yeah, because white is 255, it was getting truncated down to 200, right? So that makes sense. Okay, so now if we run this again with our newer and improved posterization algorithm, it will probably still take a minute to run, which is to be expected. But okay, cool. So hopefully this actually looks even better, right? It might be, the thing that I would say is that the whites will be a little bit darker, but the blacks will actually also be a little bit whiter. But hopefully most colors we match even a little bit better. Would you say on a whole that it's brighter? I don't know. I would say that it's less vivid, but again, I'd say that I'm colorblind. But yeah, it's going to be a little bit dependent on here, kind of in average, because on average we're going to be subtracting 32. So on average we'll add 32 back. But I would imagine it reduces the contrast for sure, which might make it feel kind of washed out. Okay, cool. So now I want us to run our most common colors algorithm again, and boom. So hopefully this palette of colors now actually looks like not too different from our image, right? Okay, sure, it's not spot on, but I would say that most of the colors that I see pop up in the original picture do show up in this palette of most common colors that we have generated. So that is, I think, where we are going to leave it today. We have learned about images and image data. We have pushed pixels around. We have implemented our own custom posterization algorithm, and we have written some functions to get the most common colors from a posterized version of an artwork. We're going to next time, our big project is going to be using these tools that we've built to build our own sort of silly first machine learning algorithm to try to identify the artist based on a work of art. And we're going to play around with that and see, I mean, honestly, kind of how hard it is and how hard it is to get good results. And then in our last session, so next session should be, even for a relative beginner, we should be able to keep it pretty accessible. But in the last session, we are going to pull all the tools out. We're going to play with all the toys. We're going to pull in Keras and TensorFlow and really try to get some good accuracy in kind of a very grown-up machine learning way. Polar Void asked, do you have any resources to go deeper into these topics? Yeah, that's a good question. I mean, so honestly, so posterization is a thing that I have looked into a little bit before. Posterization algorithms. I mean, this brings us back to Wikipedia. Let's see. Posterizing time. Yeah, so I don't have any like lying in wait. Read about this. Looking up posterization, and actually, I mean, I am sure that there are better ways to posterize. Actually, I even know better ways to posterize than what we did today. But we did something that's hopefully very simple and straightforward, and kind of gets the point across that we are reducing the diversity of colors so that we can just play with the ones that seem really important. But you absolutely could just Google, novel posterization algorithms. Would certainly be something you could look at. Another actually really cool thing to look into is different encoding algorithms. So the two big ones are PNG versus Jpeg. And this is, so we have been saying, hey, an image is a two-dimensional grid of pixels. And this is true. And in the way that we actually experience an image, this is it, right? And in all of our programming, we're going to think of them as two-dimensional arrays. But when you're storing them, you want to make them as small as possible, right? And so JPEG and PNG take different approaches to making your images small. And PNG is known as a lossless compression algorithm, so it will recreate your image exactly how it was at the beginning, whereas JPEG is allowed to throw away a little bit of information if it makes the image a lot smaller. And so this is actually a really fun deep dive to go into. I will say we don't have time for it today, but it is something that you can Google. I think there are actually really good videos on YouTube about it. And how about this? As homework for me, I'll go and try to find a good resource on learning about both posterization algorithms and PNG and JPEGs. So the final thing that I want to do is I want to, for all the real ones that stuck it out, I actually am fond of PNGs. I mean, you really need transparency, right? JPEG doesn't give you transparency. But for all the real ones that stuck around, I am going to drop our link again, which is a new link this time for a form. I would love to hear if this session was too fast or too long, or if you were just frustrated watching me debug, or maybe you enjoyed watching me debug. Maybe it was a good learning experience, or maybe it was just funny. But you can let me know that. You can also, so I pasted all of the answers from the first form of different phrases that I could tattoo onto my arm. And so I didn't filter it all. And some of them I think are actually similar. So one is a capital B blahage, and one is a lowercase, or one is technically a balage, and one is a lowercase b blahage. But you can vote for whichever one you likes. So in this form, we only have ideas that were submitted yesterday, or submitted 2 days ago, and whichever ones get the most votes today will have like a special runoff election in our next session, where we'll select the final thing that I will tattoo onto my arm. And if you tune in on Friday, I will have it tattooed and I will show it to you to prove that I did it. Cool stuff. And then as always, let me know if you have any questions or any comments on the session. Did anything work particularly well? Or did anything not work? Oh, y'all, every time I come in, I didn't even notice this time, every time I come in, they make it so that I get cropped in, and I have to turn it off every time. Yes, next time is a run-off tattoo. Oh, to be clear, not a permanent tattoo. It'll be temporary. Yes, but I don't have any tattoos as of currently. So yeah, don't get any wild ideas. But yeah, let me know if anything went well or poorly. And let me see. Let me just double check. It sounds like, yeah, we didn't have any proper questions in the last one, but if you have any questions, you can put them in that anything else you want to let me know box. It's optional. But if you do have any questions, put them in there, and I will make sure to answer all of them before we wrap up. Also, feel free to ask questions now, and in a second, I will play us off on Kalimba, just to, for me, to have a peaceful good night. Also, okay, so this is something that I just want to put out there, y'all, is that if you all vote, like, just for the one that you put down, then we're just going to be stuck in the same position. I mean, thankfully, like, right now we have 6 submissions and 6 votes for 6 different things. So I don't know. Think about if there's another one that you like. But what about the Kalimba? Oh yeah, this is my Kalimba. I'll play it for you. In fact, I'll play it for you now, so we can get calm down and peace out. Hey, okay, so thank you so much for sticking with me to the end. I really appreciate it. I had a lot of fun. Thank you for slogging with me on pushing pixels around and learning about posterization and all that good stuff. And I'm really excited that next time we're going to be able to kind of dive headfirst into thinking about machine learning and writing an algorithm and making our computers get smarter. Yeah, thank you so much for being here, and happy Monday and happy Global Hack Week. Bye, friends.